Look up at the night sky, and what do you see? Pinpricks of light, serene and unchanging, or so it seems. But the truth is far more dramatic. Every star you see is a character in an epic cosmic story, burning bright before meeting a fate as spectacular as its life. Some will fade quietly, while others explode with enough force to outshine entire galaxies. These aren't just distant points of light, they're the architects of the universe, weaving elements into existence and scattering them across the cosmos. And in their final moments, dying stars reveal secrets that rewrite the very laws of physics. Think about this: the iron in your blood, the calcium in your bones, none of it would exist without the violent deaths of stars. Supernova, neutron stars, black holes, these aren't just celestial oddities. They're the factories that forge the building blocks of planets, life, even you. It's humbling to realize we're made of stardust, but it's also awe-inspiring, because when a star dies, it doesn't just vanish. It leaves behind a legacy that shapes everything that comes after. So let's embark on a journey through time and space to witness the secret lives of dying stars. We'll explore how their final breaths create some of the most mysterious phenomena in the universe, how a collapsing star can warp space itself into a black hole, or how the remnants of a supernova can seed new solar systems. This isn't just astronomy, it's the story of how the universe recycles itself, how destruction gives birth to creation. By the end, you'll never look at the night sky the same way again. Because every star has a story, and today we're going to listen. To understand dying stars, we first need to grasp how stars live. Every star is born from vast clouds of gas and dust, collapsing under gravity until nuclear fusion ignites in its core. That fiery process turning hydrogen into helium is what makes stars shine. But just like us, stars age, and how they die depends entirely on how massive they were to begin with. Take our Sun, for example, a relatively small star. In about 5 billion years, it will exhaust its hydrogen fuel and swell into a red giant, engulfing Mercury and Venus. Eventually, it will shed its outer layers, leaving behind a dense, Earth-sized ember called a white dwarf. But for stars many times more massive than our Sun, the ending is far more explosive. When they run out of fuel, their cores collapse in seconds, triggering a supernova so bright it can outshine an entire galaxy. What's fascinating is that these dramatic deaths aren't just cosmic fireworks, they're essential to the universe's recycling process. A dying star scatters heavy elements like carbon, oxygen, and iron into space, seeding future generations of stars, planets, and even life. So when we study these stellar finales, we're not just watching an ending, we're witnessing the birth of new possibilities. The story of a star begins in the coldest, darkest places in the universe, inside vast nebulae, where clouds of gas and dust drift like cosmic ghosts. These stellar nurseries are far from empty. They're packed with the raw ingredients for star formation. When gravity gets to work pulling these particles together, the cloud begins to collapse. As it shrinks, it spins faster and heats up, forming a dense, hot core. When temperatures in that core reach a staggering 10 million degrees, something extraordinary happens. Hydrogen atoms slam together with enough force to fuse into helium. That moment when nuclear fusion ignites marks the birth of a star. For most of its life, a star exists in a delicate balance. The outward pressure from fusion fights against gravity's relentless pull, creating a stable, shining object. But nothing lasts forever, not even stars. The hydrogen fuel that powers them isn't infinite. As it runs low, the star begins to change. smaller stars like our Sun take a slow, almost graceful path to their end. After billions of years, they expand into red giants, their outer layers puffing outward while their cores contract. Eventually, those outer layers drift away, forming beautiful planetary nebulae, glowing shells of gas lit by the dying ember at their center. All that remains is a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years. But for massive stars, death is anything but quiet. These cosmic giants burn through their fuel at a furious pace, living fast and dying young. When they finally exhaust their hydrogen, they don't just swell, they go out in a blaze of glory. The core collapses in seconds, triggering a supernova explosion so powerful it can outshine an entire galaxy for weeks. In that blinding flash, elements heavier than iron are forged gold, platinum, uranium, and flung into space. What's left behind depends on the star's original size. Some become neutron stars, city-sized objects so dense that a single teaspoon of their material would weigh billions of tons. Others collapse completely, forming black holes, regions where gravity is so strong not even light can escape. What's truly remarkable is how these deaths shape the universe. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of it was forged in the hearts of dying stars. Every time we look up at the night sky, we're seeing the aftermath of these cosmic explosions, the scattered remains that will one day form new stars, new planets, perhaps even new life. The cycle continues unbroken across billions of years. Red giants may seem like the gentle elders of the cosmos, but don't let their slow, graceful demise fool you. Their final act reshapes the universe in profound ways. Picture a star like our Sun, after billions of years of steady burning, finally exhausting the hydrogen in its core. Without that outward pressure from fusion, gravity gains the upper hand, compressing the core until it grows hot enough to fuse helium into carbon. Meanwhile, the outer layers expand outward, swelling hundreds of times wider than the star's original size. This is the red giant phase, a star's last luminous breath before fading away. What happens next is both beautiful and destructive. As the red giant grows, its outer layers become unstable, puffing away into space like cosmic smoke rings. These expelled gases form intricate, glowing shells called planetary nebulae, misnamed by early astronomers who thought they resembled planets. But there's nothing planetary about them. These nebulae are stellar gravestones, lit by the intense ultraviolet radiation of the dying star's exposed core. Over thousands of years, the nebula dissipates, scattering its enriched material across the galaxy. And that's where the magic happens. Inside those drifting clouds are elements like carbon, nitrogen, and oxygen, ingredients essential for rocky planets and organic molecules. Without red giants scattering these elements into the void, Earth might never have formed, and life as we know it wouldn't exist. Even the diamond on your finger likely contains carbon forged in a red giant's core. But while these stars die quietly compared to their massive cousins, their influence is anything but small. They're the universe's recyclers, turning stellar ashes into the seeds of new beginnings. Now contrast that with supergiants, the titans of the stellar world. These behemoths live fast, burn bright, and bow out in the most spectacular fashion imaginable. When a supergiant nears the end of its life, it doesn't gently expand, it becomes a cosmic pressure cooker, fusing heavier and heavier elements in its core until it's left with a ticking time bomb of iron. And that's when the real fireworks begin. Unlike red giants, supergiants don't fade away. They go out with a bang so colossal it can be seen across the universe. But that's a story for the next chapter of our cosmic journey. Supergiants are the universe's ultimate overachievers, stars so massive they make our sun look like a flickering candle. Imagine a stellar behemoth, tens or even hundreds of times heavier than the sun, burning through its fuel not in billions of years, but in mere millions. These titans live fast, shine blindingly bright, and bow out in the most catastrophic way possible. Unlike their smaller cousins, supergiants don't just fade away. They explode with such violence that the shockwaves ripple across galaxies, leaving behind either an impossibly dense neutron star or a gravitational abyss, a black hole. The key to their explosive end lies in their cores. While smaller stars like our Sun fuse hydrogen into helium, then helium into carbon, supergiants keep going, forging heavier elements like neon, oxygen, and silicon in a desperate bid to stave off collapse. But there's a limit. When the core finally fills with iron, the star's fate is sealed. Iron is a cosmic dead end. It absorbs energy instead of releasing it during fusion. Without that outward pressure, gravity wins in an instant. The core collapses at nearly a quarter the speed of light, cramming a mass greater than the sun into a sphere no wider than a city. Then comes the supernova. In less than a second, the collapsing core rebounds off itself, sending a shockwave so powerful it rips the star apart. The explosion outshines entire galaxies, briefly becoming the brightest object in the universe. For weeks, it can glow brighter than a billion suns, but the real magic happens in those searing moments. Elements heavier than iron, like gold, platinum, and uranium, are forged in the chaos and flung into space. Every piece of jewelry, every electronic device containing these rare metals exists because of supernova. What remains after the fireworks depends on the star's original size. For slightly smaller supergiants, the core becomes a neutron star. A teaspoon of its material would weigh 1 billion tons on Earth. But for the most massive stars, not even neutrons can withstand the crush. The core collapses endlessly, warping space-time until nothing, not even light, can escape. A black hole is born, yet even in death, supergiants shape the cosmos. The heavy elements they scatter become the building blocks of new stars, planets, and life itself. Their explosions trigger the birth of nearby stars by compressing surrounding gas clouds. And the extreme environments around neutron stars and black holes, they're laboratories for physics we can't recreate on Earth, bending the laws of nature in ways that still baffle scientists. So the next time you gaze at the night sky, remember, some of those twinkling lights are supergiants, ticking time bombs waiting to rewrite the story of the universe in a single, dazzling flash. Their deaths aren't endings, they're the universe's way of reinventing itself. Supernova are nature's ultimate paradox, catastrophic endings that spark new beginnings. When one of these stellar explosions tears through space, it releases more energy in seconds than our sun will emit in its entire 10 billion-year lifetime. The flash is so intense it can briefly outshine every star in its host galaxy combined. But what makes supernova truly extraordinary isn't just their raw power, it's what they leave behind. Take neutron stars, for example. Born from the collapsed cores of massive stars, these city-sized objects pack more mass than the sun into a sphere no wider than Manhattan. The physics here defies imagination. A single sugar cube-sized chunk of neutron star material would weigh as much as Mount Everest. Their surfaces are so dense that the gravity warps light itself, creating bizarre visual distortions if you could somehow observe one up close. Some neutron stars, called pulsars, spin hundreds of times per second, sweeping beams of radiation across the cosmos like interstellar lighthouses. Then there are black holes, supernova's most enigmatic offspring. When the most massive stars explode, their cores don't stop collapsing at the neutron star stage. They keep compressing until space-time folds in on itself, creating a point of infinite density called a singularity. The gravitational pull is so strong that not even light can escape beyond the event horizon, making black holes the universe's ultimate one-way doors. Yet even these cosmic vacuum cleaners play a creative role. The superheated material spiraling into them forms brilliant accretion disks, some of the brightest objects in the universe, while the jets they shoot out can travel millions of light years, shaping entire galaxy clusters. What's remarkable is how these remnants continue shaping the cosmos long after the supernova's light fades. Neutron stars collide, spraying space with gold and platinum. Black holes merge, sending ripples through space-time itself, gravitational waves we can now detect here on Earth. These events aren't just footnotes in astrophysics, they're proof that death in the universe is never truly an end. It's a transformation, one that builds the very framework of reality. And here's the most humbling thought: without supernova and their aftermath, we wouldn't exist. The calcium in our bones, the iron in our blood, these elements were forged in stellar explosions and scattered across the galaxy by their remnants. Every time astronomers discover a new pulsar or map a black hole's shadow, we're not just studying distant curiosities. We're piecing together the story of our own cosmic ancestry. The universe writes its history in stardust and gravity, and supernova are the pen. Neutron stars are the universe's ultimate cosmic pressure cookers, stellar remnants so dense they defy logic. Picture squeezing 1.5 times the mass of our Sun into a sphere no wider than a city like New York. The result: an object where gravity is strong enough to crush atoms themselves, forcing protons and electrons to merge into neutrons. That's how neutron stars get their name and their mind-bending properties. A single teaspoon of this material would weigh around 1 billion tons on Earth. If you could somehow scoop a handful, it would slice through our planet like a hot knife through butter, pulled downward by its own unimaginable density. But neutron stars aren't just bizarre curiosities, they're cosmic powerhouses. Some, known as pulsars, spin at dizzying speeds, rotating hundreds of times per second. With each revolution, they emit beams of radiation from their magnetic poles, sweeping across space like interstellar lighthouses. These pulses are so precise that when astronomers first detected them in the 1960s, they jokingly nicknamed them LGM signals, short for little green men, because the regularity seemed almost artificial. Today, we know these celestial metronomes are natural, but no less extraordinary. Then there are magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. These fields are so intense they could erase credit card data from halfway across the solar system. Occasionally, magnetars release starquakes, cracking their rigid crusts and unleashing bursts of gamma rays bright enough to briefly outshine the entire Milky Way. But perhaps the most astonishing thing about neutron stars is how they push the limits of physics. At their cores, matter may dissolve into a strange, soupy state called nuclear pasta, where protons and neutrons arrange themselves into shapes resembling spaghetti or lasagna sheets under the crushing pressure. Some theories even suggest quarks, the fundamental particles inside protons and neutrons, might break free, creating an exotic quark-gluon plasma. Yet for all their resilience, even neutron stars have a breaking point. When two of them collide, the resulting explosion, a kilonova, scatters heavy elements like gold and platinum across space. And if a neutron star grows too massive, either by feeding off a companion star or merging with another, it can collapse further, vanishing into the ultimate cosmic abyss, a black hole. This transition marks the boundary where gravity wins completely, warping space-time into a singularity where all known laws of physics break down. So while neutron stars may be the densest objects we can directly observe, they are also cosmic stepping stones, reminders that the universe always finds a way to push matter beyond the brink of what we thought possible. Black holes are the universe's ultimate enigmas, cosmic traps where the normal rules of physics break down completely. Picture a place where gravity isn't just strong, but infinitely powerful, warping space and time to the point where the future itself bends toward the singularity at its core. This isn't science fiction, it's the inevitable fate of the most massive stars when they die. When a star many times heavier than our Sun collapses, it doesn't just form a neutron star, it keeps compressing until space-time folds in on itself, creating a point of infinite density. The boundary around this abyss, known as the event horizon, marks the point of no return. Cross it, and not even light has enough speed to escape. But black holes are far more than just cosmic vacuum cleaners. Surrounding many of them are swirling maelstroms of superheated gas and dust called accretion disks. As material spirals inward at nearly the speed of light, friction heats it to millions of degrees, making these disks some of the brightest objects in the universe. In some cases, black holes channel this energy into narrow jets that blast outward for thousands of light years, carving through galaxies like celestial blowtorches. At the center of many galaxies, including our own Milky Way, lurks a supermassive black hole, a monster millions or even billions of times heavier than the Sun. These giants didn't form from a single star's collapse but grew by merging with smaller black holes and devouring surrounding matter over eons. What's truly mind-blowing is how these gravitational behemoths shape the cosmos around them. Galaxies with active supermassive black holes at their cores often exhibit intense radiation outbursts, powering phenomena like quasars, objects so bright they outshine all the stars in their host galaxies combined. Yet paradoxically, these same black holes may also regulate star formation. Their powerful jets can heat up or expel gas from a galaxy, preventing new stars from forming too quickly. In this way, black holes act as cosmic architects, influencing the birth and evolution of entire galaxies. Even more fascinating is what happens when two black holes collide. These mergers send ripples through the fabric of space-time itself, gravitational waves that astronomers can now detect with instruments like LIGO. Each collision provides a glimpse into the extreme physics governing these objects, revealing details about their masses, spins, and the violent processes that forge them. And while black holes may seem like the end of the story, they're really just another chapter in the universe's grand recycling scheme. The material they consume doesn't vanish forever. Some of it gets ejected back into space, seeding future generations of stars and planets. So the next time you hear about a black hole, remember, they're not just cosmic destroyers, they're engines of creation, shaping the universe in ways we're only beginning to understand. From powering the brightest objects in the cosmos to sculpting the galaxies that house them, black holes prove that even in the darkest corners of space, there's more going on than meets the eye. And as we'll see next, their influence extends far beyond their own event horizons, weaving them into the very fabric of galactic evolution. Stellar remnants aren't just relics of the past, they're active players in the cosmic drama unfolding around them. When a massive star explodes as a supernova, it doesn't just vanish. It floods its surroundings with heavy elements, enriching clouds of gas and dust that will one day collapse into new stars and planets. This cycle of destruction and rebirth is the engine driving galactic evolution. Take the Orion Nebula, for instance, a bustling stellar nursery where young stars blaze to life amidst the ashes of long-dead predecessors. The iron in those stars, the oxygen in their future planets, even the silicon in their asteroids, all of it was forged in the hearts of earlier generations of stars that met explosive ends. But the influence of stellar remnants goes far beyond chemistry. Neutron stars and black holes exert gravitational forces so powerful they can redirect the motion of nearby stars, like cosmic puppeteers pulling invisible strings. In dense star clusters, these compact objects often lurk at the center, their gravity shaping the orbits of thousands of stars around them. Over millions of years, these interactions can fling stars out of their galaxies entirely, sending them hurtling into intergalactic space as rogue wanderers. Other stars get nudged into new orbits, subtly rearranging the structure of their host galaxy. On even grander scales, supermassive black holes, those lurking in galactic centers, play an even more dramatic role. When these monsters feed, they unleash torrents of energy that can heat surrounding gas to millions of degrees, preventing it from cooling and forming new stars. In some cases, their jets punch through galactic gas clouds like cosmic blowtorches, carving out vast cavities and regulating star formation across entire galaxies. It's a delicate balance. Too much activity from the black hole and star formation shuts down. Too little, and galaxies might overproduce stars, exhausting their gas reserves too quickly. The story doesn't end there. When galaxies collide, a slow-motion dance lasting hundreds of millions of years, their central black holes eventually spiral together and merge, releasing gravitational waves that ripple across the universe. These cataclysmic events can kick the newly formed black hole out of the galactic center, sending it careening through its host galaxy like a cosmic cannonball, disrupting everything in its path. Meanwhile, the shockwaves from the collision trigger bursts of new star formation, lighting up the merged galaxy with brilliant blue clusters of young stars. What's astonishing is how interconnected these processes are. The death of a single star can seed future generations of planets. A neutron star's gravity can reshape stellar neighborhoods. A supermassive black hole's appetite can determine whether a galaxy thrives or stagnates. Across billions of years, these interactions weave together, creating the rich tapestry of galaxies we see today. Without stellar death, there would be no stellar birth, no planets, no life, no cosmic diversity. The universe would be a far quieter, darker, and emptier place. So when we look at distant galaxies through our telescopes, we're not just seeing static snapshots, we're witnessing an ongoing story of transformation, written in the lives and deaths of stars. Each explosion, each collision, each quiet fade into darkness is a sentence in that story. And as we piece together these cosmic narratives, we begin to understand our own place in the grand scheme, a fleeting moment in a saga that spans eternity. Galaxies are the grand theaters where this cosmic recycling plays out, but not all stages are the same. In the spiraling arms of galaxies like our Milky Way, where gas and dust are plentiful, dying stars continuously seed their surroundings with heavy elements. Each supernova explosion acts like a celestial sprinkler system, spraying gold, platinum, and uranium into nearby clouds. Over time, these enriched pockets collapse under gravity, birthing new stars already laced with the ingredients for rocky planets and potentially life. But step into an elliptical galaxy where star formation has nearly ceased and the story changes. Here, the remains of ancient stars drift in a sparse sea of old, red suns, their heavy elements locked away in aging stellar bodies rather than being recycled into new ones. The most extreme environments are dwarf galaxies, tiny cosmic backwaters where even a single supernova can reshape the entire system. Without the gravity to hold onto their gas, these small galaxies often lose their enriched material to intergalactic space, blown away by the very explosions that created it. It's a paradox. The stars that forge the building blocks of life can also strip their homes of the resources needed to use them. Yet occasionally, these expelled elements catch rides on galactic winds, eventually mingling with larger galaxies in a slow-motion transfer of cosmic wealth. Then there's the intergalactic medium, the vast, near-empty spaces between galaxies. Though it seems barren, it's actually laced with traces of iron, oxygen, and carbon, ejected by dying stars over billions of years. Even here, far from any stellar nursery, the legacy of stellar deaths lingers. When galaxies collide, these tenuous clouds can ignite sudden bursts of star formation, proving that no element ever truly leaves the cycle. What's astonishing is how finely tuned this process is. Too few supernova, and the universe would lack the diversity of elements needed for complex chemistry. Too many, and radiation could sterilize entire galaxies. It's a balancing act that's played out differently in every corner of the cosmos, creating pockets where life might flourish and others where it never gets the chance. As we peer deeper into distant galaxies, we're not just mapping stars, we're tracing the intricate pathways of cosmic renewal, where every explosion writes another line in the universe's recipe book. Spiral galaxies like our Milky Way are cosmic engines of perpetual change, where the deaths of stars fuel new beginnings in an endless cycle. Picture the vibrant arms of a spiral galaxy, glowing with the pinkish hue of hydrogen gas, the raw material for star formation. Within these stellar nurseries, massive stars burn bright and die young, their explosive supernovas sending shockwaves through nearby gas clouds. Like a cosmic domino effect, these shockwaves compress the gas, triggering the collapse of new protostars. It's a breathtaking feedback loop. Stellar deaths literally give birth to the next generation, but not all stellar farewells in spiral galaxies are violent. Sun-like stars take a gentler exit, swelling into red giants before shedding their outer layers as delicate planetary nebulae. These slower deaths are no less important. While they lack the spectacle of supernova, they're prolific producers of carbon, nitrogen, and oxygen, elements essential for organic chemistry. Over billions of years, countless quiet deaths like these have enriched the Milky Way's interstellar medium, turning primordial hydrogen and helium into a diverse chemical palette. The contrast with elliptical galaxies couldn't be starker. Imagine a galaxy where star formation has all but ceased, a realm of aging red stars drifting in a sparse, gas-deprived environment. Here, supernovae are rare, and the few that occur scatter their heavy elements into a near vacuum, with little gas left to form new stars, the result. A galaxy frozen in time, its stellar population growing older and redder with no fresh generations to replace them. Yet even in these quiet giants, stellar deaths leave a mark. Over eons, the slow accumulation of planetary nebula ejections and the occasional supernova subtly alter the galaxy's chemistry. Without the constant churn of spiral arms, these changes accumulate like sediment in a still lake, layer upon layer, barely noticeable until millennia have passed. What's truly remarkable is how these differences shape galactic evolution. Spiral galaxies, with their dynamic cycles of birth and death, remain vibrant and chemically diverse. Ellipticals, though majestic in their own right, are like cosmic museums preserving the relics of a more active past. Together, they show us the many ways a galaxy can grow old, each path leaving its own unique fingerprint on the universe. Elliptical galaxies are the quiet elders of the cosmos, vast, golden-hued islands where stellar drama unfolds at a glacial pace. Unlike the vibrant whirlpools of spiral galaxies, these smooth, football-shaped giants burned through their star-forming gas long ago. Here, the night sky would appear strikingly different from our Milky Way's star-studded tapestry. Instead of brilliant blue young stars, elliptical galaxies glow with the steady light of aging red suns. their populations dominated by ancient stars that formed in a frenzied burst of activity billions of years earlier. The deaths of stars in these galaxies are seldom explosive. Without massive young stars to go supernova, elliptical galaxies witness far fewer cosmic fireworks. Instead, their stellar farewells are slow and methodical. Most stars here end their lives as white dwarfs, Earth-sized embers that fade over trillions of years, their heat leaking into the frigid depths of space. Occasionally, two white dwarfs will spiral together in a silent dance, merging to reignite nuclear fusion in a final, fleeting blaze called a Type Ia supernova. These explosions are critical cosmic mile markers, their consistent brightness allowing astronomers to measure vast distances across the universe. But elliptical galaxies hold more than just fading stars. Deep within their crowded cores, neutron stars, the dense remnants of long-dead massive stars, occasionally collide. When these ultra-dense objects merge, they unleash kilonovae, explosions that spray space with gold, platinum, and other heavy elements. Unlike the chaotic star-forming regions of spiral galaxies, where such events might go unnoticed amidst the stellar chaos, kilonovae in elliptical galaxies stand out starkly against the quiet backdrop. What makes these galaxies truly special is their role as cosmic time capsules. The stars here formed when the universe was young, their chemical makeup preserving the conditions of the early cosmos. By studying them, astronomers can peer back to an era when galaxies were first assembling, tracing how generations of stellar deaths gradually enriched the universe with heavier elements. Yet even in these seemingly static environments, change is constant. The slow accumulation of stellar remnants, white dwarfs, neutron stars, and black holes subtly alters the galaxy's gravitational field over eons. Some theorists suggest that the supermassive black holes at the centers of elliptical galaxies grew not just by swallowing gas, but by devouring countless stellar corpses over billions of years. So while elliptical galaxies may lack the dazzling stellar nurseries of their spiral cousins, they offer something equally valuable, a window into the universe's past. Their quiet, steady evolution reminds us that cosmic history isn't written solely in violent explosions, but also in the patient accumulation of whispers across time. And as we'll soon see, even these quiet giants have their extremes where stellar deaths push the limits of physics in ways that defy imagination. Hypernova rewrite the rules of cosmic destruction. These aren't just supernova with extra fireworks, but total stellar obliteration on a scale that defies comprehension. Picture a star so massive that when its core collapses, it doesn't just form a black hole. It triggers a pair of relativistic jets, narrow beams of energy screaming outward at 99.9% the speed of light. These jets, packed with gamma rays, are the universe's ultimate death rays. If one were pointed at Earth from thousands of light years away, it could strip our atmosphere of ozone in seconds, triggering mass extinctions. Fortunately, hypernova are rare, occurring perhaps once every million years in a galaxy like ours. What makes gamma-ray bursts so fascinating isn't just their power, it's their precision. Unlike a supernova's spherical explosion, hypernova channel their energy into those twin jets, focusing it like a cosmic blowtorch. When we detect a GRB, we're essentially seeing a lighthouse beam sweeping across the universe, visible only if we're lined up with its path. The afterglow, a fading echo of X-rays and visible light, can last for weeks, allowing astronomers to study the wreckage in unprecedented detail. Some of these bursts originate from galaxies in the early universe, their light traveling for billions of years before reaching us. That means we're witnessing the deaths of stars that died before our solar system even existed. But hypernova aren't just destructive, they're creative. The same jets that could sterilize planets also forge elements heavier than iron, like gold and platinum, in quantities far exceeding ordinary supernova. Without these cataclysms, the universe might lack the precious metals we mine for jewelry and electronics. Even more remarkably, some theorists suggest that GRBs could play a role in seeding life. The intense radiation might kickstart chemical reactions in distant nebulae, creating complex molecules that later become the building blocks of planets. Then there are the quieter, more enigmatic stellar deaths events that don't light up the cosmos with gamma rays but still baffle scientists. Take blue supergiants, for example. These massive stars occasionally vanish without a trace, collapsing directly into black holes without the customary supernova fanfare. It's as if the universe flipped a switch, turning off a star mid-shine. Other stars, like Wolf-Rayets, shed their outer layers so violently they resemble cosmic smoke rings, leaving behind exposed cores that glow with eerie intensity. What ties these extremes together is gravity's relentless pull. Whether a star dies in a hypernova's blaze or fades silently into a black hole, its fate hinges on the same cosmic scale's mass, rotation, and the delicate balance of forces in its core. And while hypernova dominate the headlines, their quieter counterparts remind us that the universe harbors just as many mysteries in the shadows as it does in the light. Each stellar death, whether deafening or silent, peels back another layer of the cosmos' secrets, and we're only beginning to listen. White dwarfs are the universe's quiet retirees, stellar embers glowing faintly with the leftover heat of a life spent burning brightly. Imagine the core of a star like our Sun, stripped of its outer layers after the red giant phase, compressed into a sphere no larger than Earth yet containing half the original star's mass. The physics here is staggering. A single teaspoon of white dwarf material would weigh several tons, crushed to densities 1,000,000 times greater than anything on Earth. But unlike their massive cousins, these remnants don't explode or collapse further, they simply cool, fading over trillions of years like cosmic coals. Yet even in their stillness, white dwarfs hold surprises. Some don't fade quietly. When a white dwarf orbits a companion star, it can siphon off gas, gradually accumulating material on its surface. Over time, the pressure and heat at its core build until suddenly, carbon fusion reignites. The result, a Type Ia supernova, a thermonuclear detonation so powerful it outshines entire galaxies. What makes these explosions invaluable to astronomers is their consistency. Unlike other supernova, which vary widely in brightness, Type Ia events always release roughly the same amount of energy. This predictability makes them cosmic mile markers, allowing scientists to measure distances across the universe with precision. But the drama doesn't end there. When two white dwarfs spiral toward each other in a gravitational dance, their collision can trigger an even more spectacular explosion. Picture two Earth-sized stars, each denser than anything in our solar system, smashing together at thousands of miles per second. The impact unleashes a supernova rivaling the brightness of 100 billion suns, scattering elements like iron and silicon across interstellar space. These rare events are thought to be responsible for much of the iron in the universe, the same iron that courses through your veins right now. Then there are the outliers, white dwarfs that defy expectations. Some, known as zombie stars, survive partial supernova, their cores intact even after expelling their outer layers. Others, called magnetic white dwarfs, possess fields trillions of times stronger than Earth's, warping the space around them into bizarre configurations. And in the far future, when the universe has grown cold and dark, white dwarfs may be the last sources of light, their faint glow persisting long after all other stars have burned out. So while white dwarfs may seem like the quiet end to stellar lives, they're anything but simple. Whether they're serving as cosmic measuring sticks, colliding in cataclysmic explosions, or clinging to existence as the universe's final beacons, these dense remnants prove that even in death, stars find ways to shape the cosmos. And in their slow fade to black, they carry with them the echoes of the universe's fiery beginnings. Type Ia supernova are the universe's ultimate cosmic yardstick stellar explosions, so consistent they've reshaped our understanding of space itself. Picture a white dwarf, the dense remnant of a star like our Sun, quietly orbiting a companion star. Over thousands of years, it siphons off hydrogen or helium from its neighbor, packing more and more material onto its surface. The pressure builds until, suddenly, carbon fusion reignites in its core. But unlike the steady burning of a living star, this fusion spreads uncontrollably, detonating the entire white dwarf in a thermonuclear blast brighter than 1 billion suns. What makes these explosions special isn't just their power, it's their predictability. Every Type Ia supernova peaks at nearly the same intrinsic brightness, like cosmic lighthouses flashing with identical intensity. This consistency is a gift to astronomers. By comparing how bright these supernovae appear from Earth to how bright they actually are, scientists can calculate their distance with remarkable precision. In the 1990s, observations of distant Type Ia supernova led to a shocking discovery. The universe isn't just expanding, it's accelerating. Some mysterious force, now called dark energy, is pushing galaxies apart faster and faster. Without these stellar explosions acting as mile markers, we might never have uncovered one of cosmology's greatest mysteries. But Type Ia supernova aren't just measuring tools, they're also cosmic blacksmiths. Each explosion forges roughly half a solar mass of iron, scattering it across galaxies. The iron in your car, your skyscraper, even the hemoglobin in your blood, likely originated in a cataclysm like this billions of years ago. Yet for all their destructive power, these events are strangely precise. The white dwarf must grow to nearly 1.4 times the Sun's mass, a limit called the Chandrasekhar limit, before it can explode. Teeter just below that threshold, and the star remains stable. Cross it, and the universe gains a new yardstick. Not all white dwarfs reach this fate, though. Some exist in binary systems where their companion star isn't generous enough to feed them the mass they need. Others drift alone through the galaxy, cooling slowly into black dwarfs over trillions of years, a fate so slow that none exist yet in our 13.8 billion-year-old universe. Then there are the true oddballs, white dwarfs that avoid explosion by colliding with other white dwarfs first. When two of these dense remnants spiral together, they might merge into a single, more massive star, or, if their combined mass exceeds the Chandrasekhar limit, trigger a supernova even more spectacular than the standard Type Ia. But perhaps the strangest white dwarfs are those that cheat death entirely. A handful have been caught surviving partial supernova, their cores intact even after expelling their outer layers. Astronomers call them zombie stars, stellar remnants that somehow endure what should have been total annihilation. These cosmic survivors challenge our understanding of how white dwarfs explode, proving that even the most predictable stellar deaths can harbor surprises. And as we peer deeper into the universe, each new supernova reveals another piece of the puzzle, not just about how stars die, but how their deaths light the way for discovery. Black dwarfs are the universe's final whisper, theoretical remnants of stars that have burned out completely, fading into darkness after trillions of years of cooling. Imagine a white dwarf once glowing with residual heat, now so cold it emits no light at all, drifting through space as a frozen, Earth-sized cinder. These objects don't exist yet. The universe simply hasn't had enough time for even the oldest white dwarfs to cool to absolute zero. In fact, calculations suggest the first black dwarfs won't appear for another 10 to the 15th power years, a number so vast it dwarfs the current age of the cosmos by orders of magnitude. Yet this distant fate tells us something profound about the universe's timeline. Most stars, 97% of them, will eventually become black dwarfs, their light extinguished forever. Our own sun is destined for this quiet end, a far cry from the explosive deaths of massive stars. But while black dwarfs represent the ultimate fade out, their journey there is anything but uneventful. Long before reaching total darkness, white dwarfs interact with their surroundings in subtle but fascinating ways. Some, like the famous Sirius B, orbit brighter companion stars, their gravitational influence betraying their presence even as they cool. Others wander alone, their strong magnetic fields warping nearby space like invisible fingerprints. What's intriguing is how these fading embers still shape their cosmic neighborhoods. A white dwarf's gravity can perturb passing comets or asteroids, flinging them toward inner planetary systems or devouring them entirely. In fact, astronomers have spotted white dwarfs with polluted atmospheres, their spectra revealing traces of heavy elements like calcium and iron. These are the ghosts of planets, asteroids, or even moons that spiraled too close and were torn apart by tidal forces, their debris raining onto the dead star's surface. It's a stark reminder that even in death, stars continue to interact with their environments, rewriting the stories of the systems they once ruled. And then there's the far future, when black dwarfs will dominate a cold, dark universe. By then, star formation will have ceased, galaxies will have evaporated, and the cosmos will be a graveyard of these silent remnants. Yet even in this bleak scenario, black dwarfs might still play a role. Some theories suggest they could collide over unimaginable timescales, triggering faint flashes in the void, the last bursts of light in an otherwise endless night. Others might slowly evaporate due to quantum effects, their particles leaking away into nothingness. But before we dwell on that distant twilight, let's turn our gaze back to the vibrant present, where dying stars are anything but silent. From the shockwaves of supernova to the gravitational ripples of merging neutron stars, the universe is alive with stellar finales that shape the cosmos here and now. These events aren't just endings, they're the catalysts for new beginnings, proving that even in death, stars never truly fade away. They transform, they scatter, they rebuild. And in doing so, they ensure the universe remains a place of endless change. Planetary nebulae are the universe's stained glass windows, celestial masterpieces painted by dying stars in their final act. When a star like our Sun reaches the end of its life, it doesn't explode dramatically like a supernova. Instead, it swells into a red giant, pulsating as it sheds layer after layer of gas into space. These expelled layers don't just drift away aimlessly. They form intricate, glowing structures that can span light years, illuminated by the intense ultraviolet radiation from the exposed stellar core. What's astonishing is the sheer variety of shapes. Some nebulae resemble butterflies, others look like eyeballs or even hourglasses. The secret behind these stunning forms lies in the star's death throes. As the red giant loses mass, its core becomes unstable, ejecting material in erratic bursts. But it's not just a simple outward flow. Many stars have companion stars or planets whose gravity sculpts the escaping gas into delicate loops and spirals. Magnetic fields also play a role, channeling charged particles into jets that carve out bipolar structures. Even the star's rotation matters. Spinning faster can flatten the nebula into disc-like shapes, while slower rotation allows for more spherical expansions. What makes these nebulae truly special isn't just their beauty. It's their role as cosmic recyclers. The gas they expel is rich in carbon, nitrogen, and oxygen, elements essential for rocky planets and organic chemistry. Over millions of years, this material mingles with interstellar clouds, eventually becoming part of new stars, planets, and even life. The Ring Nebula, for instance, contains enough carbon to seed thousands of future solar systems. Yet planetary nebulae are fleeting. After just a few tens of thousands of years, a blink in cosmic time, the gas dissipates, fading into the interstellar medium. The white dwarf at the center remains, cooling slowly over billions of years. But for that brief, luminous moment, a dying star transforms into one of the most breathtaking sights in the universe, proving that even in death there is artistry. Stellar winds are the silent sculptors of a star's fate, invisible currents that carry away a star's very essence over millions of years. Picture the sun, not as the steady beacon we know, but as a dynamic force constantly shedding particles into space. This solar wind, gentle by cosmic standards, still manages to strip away about 1 million tons of material every second. Now imagine a red giant, its outer layers so loosely bound that radiation pressure lifts gas and dust into space like cosmic confetti. These aren't gentle breezes but gales roaring at hundreds of thousands of miles per hour, carrying entire Earth masses of material into the void annually. The mechanics behind this mass loss are as elegant as they are relentless. Photons, particles of light, streaming from the star's core, collide with atoms in its outer layers, transferring momentum like billions of microscopic billiard balls. Over time, this radiation pressure overcomes gravity's grip, launching material outward. For massive stars, the effect is even more dramatic. Their intense ultraviolet radiation ionizes surrounding gas, creating stellar winds so powerful they can carve vast cavities in nearby nebulae, like cosmic sandblasters etching patterns across the sky. But stellar winds don't flow uniformly. A star's rotation and magnetic field twist these outflows into spiraling corridors, shaping the eventual nebula like invisible hands molding clay. Some stars, particularly those with strong magnetic fields, channel their winds into bipolar jets, twin beams of particles shooting from their poles. When these fast winds eventually collide with slower-moving material ejected earlier, shockwaves ripple through the gas, compressing it into the intricate shells and filaments seen in planetary nebulae. The famous Cat's Eye Nebula, with its concentric rings and spikes, is essentially a fossilized record of its central star's changing wind patterns over millennia. Mass loss isn't just a cosmetic process, it's a cosmic countdown timer for stellar death. How much material a star sheds determines whether it ends as a white dwarf, neutron star, or black hole. Take Wolf-Rayet stars, for example. These massive, short-lived stars lose so much mass so quickly that they effectively strip themselves naked, ejecting whole solar masses in just 100,000 years. By the time they explode as supernova, they've already returned much of their substance to the galaxy, leaving behind a lean core primed for collapse. Now imagine introducing a second star into this delicate dance. Binary systems add turbulence to an already complex process, with gravitational interactions that can warp stellar winds into bizarre, asymmetrical shapes. In some cases, the companion star's gravity funnels the dying star's outflow into a dense disk, later powering spectacular jets perpendicular to the orbital plane. Other times, the stars trade material back and forth in a celestial tug of war, dramatically altering each other's life cycles. These interactions don't just create beautiful nebulae, they can trigger supernova centuries ahead of schedule or produce exotic stellar remnants unlike anything seen in single-star systems. The story of stellar winds is ultimately one of transformation of how stars, through their slow exhale into the void, rewrite their own destinies while seeding the galaxy with the raw materials for new beginnings. Every atom carried away on these cosmic breezes is a promise, a piece of the star that will one day become part of something new. Binary stars transform stellar death into a cosmic ballet where gravity's pull and stellar proximity rewrite the rules of how stars meet their end. Picture two stars locked in orbit, one a massive giant, the other a dense white dwarf. As the giant swells in its death throes, its outer layers spill toward the dwarf, a slow-motion transfer of stellar material that can trigger a cataclysm. This isn't just a gentle exchange, it's a prelude to one of the universe's most precise explosions, the Type Ia supernova. When the white dwarf reaches a critical mass, its carbon core detonates with such consistency that astronomers use these blasts as cosmic measuring tapes, charting the expansion of the universe itself. But binary systems don't always end in fire. Sometimes they end in a collision. Take neutron stars, the ultra-dense remnants of massive stars. When two of these objects spiral toward each other, their merger sends ripples through space-time gravitational waves detectable across billions of light years. The aftermath is a kilonova, an explosion that forges gold, platinum, and other heavy elements in quantities far exceeding ordinary supernova. The 2017 detection of such an event marked a new era in astronomy, proving that these rare collisions are cosmic gold mines, literally. Yet not all stars have partners. Solitary stars face death on their own terms, their fates dictated solely by their mass. A lone red giant sheds its layers quietly, its expelled gas forming a planetary nebula without the gravitational interference of a companion. Its core cools into a white dwarf, destined to fade into oblivion over trillions of years. Meanwhile, an isolated massive star might collapse directly into a black hole, its supernova muted or even skipped entirely, a silent vanishing act that leaves no spectacular light show, just an invisible gravitational pit in space. The contrast between these solitary deaths and the drama of binary systems couldn't be starker. One is a solo performance, slow and methodical. The other, a chaotic duet where gravity's pull turns stellar demise into a spectacle. But both paths are essential to the universe's story. Binary interactions seed the cosmos with rare elements and illuminate the darkest corners of physics, while solitary stars remind us that even in isolation, the universe finds ways to recycle, transform, and endure. Whether alone or entwined, every star's death leaves a marker, a ripple in the fabric of space, a scattering of stardust, or a beacon for the next generation of cosmic explorers. Lone stars chart a quieter, more solitary path through the cosmos, their life cycles unfolding without the gravitational tug of a companion to alter their fate. Take a star like our Sun, destined to spend its twilight years as a white dwarf. After billions of years of steady fusion, it will gently puff away its outer layers, leaving behind a dense, Earth-sized core that glows faintly with residual heat. Unlike stars in binary systems, which might reignite in a fiery supernova, this solitary remnant will cool in silence over trillions of years, its influence limited to the occasional gravitational nudge on passing comets or asteroids. Yet even in isolation, its legacy endures. The carbon and oxygen forged in its core now drift through space, future ingredients for new stars or planets. Massive lone stars face a more dramatic but equally lonely end, when a colossal star 20 times heavier than the Sun exhausts its fuel, its core collapses in seconds. The resulting supernova scatters iron, silicon, and heavier elements across light years, while the remnant, a neutron star or black hole, anchors the scene like a silent sentinel. Without a companion to feed it, the neutron star spins down over eons, its lighthouse beams fading. The black hole, too, sits in darkness, its gravity bending nearby starlight but otherwise invisible. Yet these isolated remnants still shape their surroundings. A neutron star's magnetic field can accelerate particles to near light speed, creating eerie glows in nearby gas clouds, while a black hole's gravity might subtly warp the orbits of distant stars over millennia. Now contrast this with the fate of stars in globular clusters, dense stellar cities where millions of stars orbit shoulder to shoulder. Here, gravitational encounters are inevitable. A white dwarf might collide with another, triggering a supernova. A neutron star could be flung into a new orbit or even captured by another star, restarting a cycle of cosmic cannibalism. The sheer density of these environments turns stellar death into a chaotic, unpredictable affair where close encounters rewrite destinies in an instant. Yet for all their differences, both path, solitary and crowded, serve the same cosmic purpose, recycling. Whether a star dies alone in the quiet outskirts of a galaxy or in the bustling core of a cluster, its elements return to the universe, fueling new generations of stars and planets. The difference lies in the drama. One is a solo sonata, precise and measured. The other, a symphony of collisions and near misses where chance encounters dictate the finale. Both remind us that in the end, no star truly dies in vain. Globular clusters are cosmic time capsules, dense, spherical swarms of hundreds of thousands of stars, all bound together by gravity in a space smaller than the distance between our Sun and its nearest stellar neighbor. Within these ancient stellar cities, stars don't die quietly. They collide, exchange material, and rewrite each other's fates in ways that would be impossible in the sparser suburbs of galaxies like our Milky Way. Picture a place where stars are packed so tightly that a single cubic light year might contain thousands of them compared to the lonely few stars that occupy the same volume near Earth. In this stellar metropolis, death isn't a solitary event. It's a communal affair where one star's demise can trigger a chain reaction of cosmic consequences. Take blue stragglers, for example, stars that appear younger and bluer than their cluster mates, defying the rules of stellar aging. These celestial anomalies are thought to form when two older stars collide or transfer mass in close encounters, merging into a single, rejuvenated star that burns hotter and brighter than either of its predecessors. It's as if two retirees teamed up to become a youthful athlete, their combined fuel reigniting nuclear fusion with fresh intensity. These stellar Frankenstein's monsters are rare elsewhere in the galaxy, but in globular clusters, they're a testament to how gravitational crowding can cheat time itself. Then there are the stellar remnants, neutron stars and white dwarfs, that linger long after their parent stars have expired. In most of the universe, these dense cinders drift alone, their influence limited to subtle gravitational tugs. But in a globular cluster, they're anything but isolated. A neutron star might capture a passing star as a companion, siphoning off its gas to become a pulsar that beams radiation across the cosmos. Two white dwarfs could spiral together over eons, merging in a cataclysmic explosion that outshines entire galaxies for weeks. Even black holes, the universe's ultimate vacuum cleaners, aren't immune to the chaos. They might slingshot each other through the cluster in a gravitational dance, ejecting some stars while flinging others into tighter orbits. What makes these clusters so valuable to astronomers isn't just their drama, it's their age. Many globular clusters formed over 12 billion years ago, making them relics of the universe's youth. By studying how stars die in these environments, we glimpse the conditions of the early cosmos, when galaxies were first assembling and the chemical makeup of the universe was far simpler. The heavy elements we take for granted, oxygen, carbon, iron, were scarce back then, meaning the deaths of early stars played an outsized role in seeding the universe with the ingredients for planets and life. Yet even in these ancient stellar crowds, mysteries abound. Some clusters have far fewer neutron stars than expected, suggesting these dense remnants might be ejected entirely during close encounters. Others harbor puzzling X-ray sources, hinting at black holes or exotic binary systems we've yet to fully understand. Each observation peels back another layer of the universe's history, revealing how stellar death shaped the cosmos long before our solar system even existed. And as we turn our gaze further back in time to the earliest stars of all, we'll see how their explosive ends lit the way for everything that followed. The first stars to ignite in the cosmos weren't just different, they were alien by today's standards. Born from pristine clouds of hydrogen and helium mere hundreds of millions of years after the Big Bang, these colossal behemoths, dubbed population Roman III stars, lacked the heavy elements that modern stars inherit. Without carbon, oxygen, or iron to help cool their birth clouds, they grew to staggering sizes, some reaching hundreds of solar masses. Their sheer bulk meant they lived fast and died young, burning through their fuel in just a few million years, a cosmic blink compared to our sun's 10 billion-year lifespan. But it's how they died that changed everything. When these primordial giants finally collapsed, their supernova were unlike anything witnessed since. Current models suggest some may have exploded as pair instability supernova, events so violent they left no remnant behind, obliterating themselves completely in blasts energetic enough to outshine entire galaxies. The shockwaves from these detonations ripped through the early universe, compressing nearby gas clouds and triggering the birth of second-generation stars. More crucially, they forged the universe's first heavy elements in their cores: carbon, nitrogen, oxygen, and scattered them across the cosmos like cosmic breadcrumbs. For the first time, the periodic table grew beyond hydrogen and helium, setting the stage for everything to come. Yet these ancient supernovae differed from modern ones in startling ways. Today's stellar explosions, like the type Roman II supernova of a massive star, leave behind neutron stars or black holes. But the first stars were so massive that some may have collapsed directly into black holes without a visible supernova at all, their cores vanishing into gravitational pits so deep even light couldn't escape. Others might have exploded with such force that they temporarily reversed the collapse itself, creating exotic hypernova that flooded space with gamma rays. The chemistry they produced was different too. Modern supernova create elements like gold and uranium through rapid neutron capture, but the first stars likely produced far fewer of these heavy metals. Instead, they focused on lighter elements, the building blocks of future rocky planets and ultimately life. Every carbon atom in your body can trace its lineage back to these primordial furnaces. What's equally fascinating is how rare these first stars would seem today. The universe has grown richer in metals over billions of years, making it nearly impossible for such pure hydrogen-helium giants to form now. Their descendants, population Roman II and I stars like our Sun, carry the chemical fingerprints of those early explosions. Even now, astronomers hunt for surviving second-generation stars in our galaxy's halo, hoping their unusual compositions will reveal secrets about the universe's first deaths. The legacy of these pioneer stars isn't just written in stardust, it's etched into the very structure of the cosmos. Their deaths cleared the cosmic fog of the early universe, allowing light to travel freely for the first time. Their explosions assembled the first heavy nuclei, enabling the diverse chemistry we take for granted, and their black hole remnants may have grown into the supermassive monsters that anchor galaxies today. They were the universe's first alchemists, turning simplicity into complexity, chaos into order, one cataclysmic death at a time. The stars we see today are fundamentally different from their primordial ancestors, not just in size or brightness, but in the very ingredients that forged them. Those first stars, born from pure hydrogen and helium, lived short, violent lives before exploding and seeding the cosmos with heavier elements. Fast forward billions of years, and modern stars like our Sun are infused with traces of carbon, oxygen, and iron elements that didn't exist in the early universe. This chemical enrichment has quietly rewritten the rules of stellar life and death. Today's stars burn cooler and longer, their atmospheres flecked with metals that help regulate their internal processes. Even their deaths are different. When a modern massive star explodes as a supernova, it doesn't just scatter simple elements. It unleashes a periodic table's worth of heavy metals, from gold to uranium, into the galactic ecosystem. The interstellar medium itself has evolved into a complex chemical soup. Gone are the pristine clouds of hydrogen that birthed the first stars. Instead, modern star-forming regions are littered with dust grains rich in silicates and carbon compounds, debris from countless past supernovae. This dust acts like a cosmic thermostat, helping gas clouds cool and collapse into new stars more efficiently than in the early universe. Even the remnants of stellar deaths have changed. Neutron stars today often form amidst this enriched environment, their intense magnetic fields interacting with heavy element debris to create bizarre phenomena like magnetars, stellar corpses with magnetic fields so strong they could distort atoms from light years away. Yet the universe isn't done evolving. Peer far enough into the future, and the cycle of stellar birth and death will slow dramatically. As galaxies exhaust their gas reserves, star formation will sputter out, leaving behind a cosmos dominated by fading stellar remnants. The last stars to ignite small, dim red dwarfs may shine for trillions of years before finally winking out. By then, the universe will be a darker, colder place, where black holes are the primary actors, slowly evaporating via Hawking radiation over unimaginable timescales. Even supernova will become rare events, their flashes standing out starkly against an increasingly static backdrop. But there's a poetic symmetry to this distant future. Just as the first stars lit up a universe emerging from darkness, the last stars will fade into a cosmos returning to stillness. The heavy elements they leave behind, forged in their cores and scattered by their deaths, will endure, drifting through space as silent witnesses to the universe's fiery past. And somewhere, perhaps, those atoms will find their way into new forms, carrying forward the legacy of stars long gone. The universe may change, but the story of stellar life and death, of endings that fuel new beginnings, remains eternal. The universe still blazes with the light of countless stars today, but trillions of years from now, the cosmic landscape will look utterly different. Imagine a time so distant that all star formation has ceased, no new suns ignite, no stellar nurseries glow with infant stars. The galaxies, once vibrant with light, will be populated only by the fading remnants of dead stars, white dwarfs cooling into obsidian like black dwarfs, neutron stars slowly losing their spin, and black holes orbiting in the darkness like silent ghosts. Even these remnants won't last forever. Over timescales that dwarf the current age of the universe, white dwarfs will radiate away their last whispers of heat. Neutron stars may decay through processes we've yet to fully understand, and black holes, those seemingly eternal gravitational pits, will evaporate particle by particle through Hawking radiation. The era of stellar deaths, so dramatic and creative today, will finally draw to a close, leaving a universe too cold and diffused to reignite the fires of nuclear fusion. Yet before that inevitable twilight, we have an extraordinary opportunity to study dying stars while the universe is still alive with them. Modern astronomy gives us front-row seats to stellar finales happening right now across the cosmos. Telescopes like Hubble and JWST capture planetary nebulae in their fleeting glory, revealing intricate structures sculpted by stellar winds. Gravitational wave detectors like LIGO and Virgo catch the ripples from neutron star collisions, events that forge gold and platinum in cosmic quantities. Even humble backyard telescopes can spot supernova lighting up distant galaxies, their brilliant flashes signaling the explosive end of a massive star. What's remarkable is how much we've learned by combining these tools. Spectroscopy breaks starlight into rainbows, revealing the chemical fingerprints of elements forged in stellar cores. Neutrino observatories detect ghostly particles streaming from supernova, offering a real-time glimpse into a collapsing star's heart. And space-based telescopes peer through dust clouds to watch young stars being born from the ashes of their predecessors, closing the cosmic recycling loop before our eyes. Perhaps the most thrilling frontier is time domain astronomy, the study of how celestial objects change over hours, days, or years. Programs like the Zwicky Transient Facility scan the skies nightly, catching stars in the act of erupting, fading, or colliding. Each alert could lead to a breakthrough, a supernova caught in its earliest moments, a white dwarf stealing mass from a companion, or even a star vanishing without a trace, suggesting a direct collapse into a black hole. These observations aren't just about cataloging events, they're stress-testing our theories about how stars live and die. So while the far future may hold a silent, dark universe, today we're living in a golden age of discovery. Every stellar death we witness adds another piece to the puzzle of cosmic evolution, helping us understand not just how stars end, but how their endings shape everything that comes after. And as our tools grow sharper, who knows what secrets these dying stars will reveal next? Peering into the final chapters of a star's life requires more than just visible light. It demands a symphony of instruments, each tuned to a different cosmic frequency. Radio telescopes, for instance, trace the faint whispers of molecular gas in planetary nebulae, revealing structures invisible to optical scopes. Infrared observatories like the James Webb Space Telescope pierce through dust clouds to expose the birthplaces of new elements in supernova remnants, while X-ray satellites catch the searing glow of million-degree gas around neutron stars and black holes. Even gamma-ray detectors play a role, spotting the violent signatures of hypernova or magnetar eruptions billions of light-years away. The Hubble Space Telescope has revolutionized our view of stellar death, capturing planetary nebulae in such detail that we can trace their intricate jets and shockwaves like forensic evidence. But JWST takes it further, dissecting the chemistry of these stellar ghosts with mid-infrared precision, spotting molecules like polycyclic aromatic hydrocarbons that hint at complex chemistry brewing in the aftermath. Meanwhile, ground-based spectrographs break starlight into rainbows, their absorption lines acting as barcodes that reveal the presence of oxygen, neon, or even gold in the ejecta. It's like cosmic archaeology, where every spectral line tells a story of nuclear fusion and explosive decay. Then there are the gravitational wave observatories like LIGO and Virgo, which don't see dying stars at all, they feel them. When two neutron stars spiral into each other, they ripple the fabric of space-time itself. The 2017 detection of such a collision wasn't just a triumph of engineering. It confirmed that these mergers are cosmic gold mines, producing enough heavy elements in seconds to outweigh entire planets. And neutrino detectors, buried deep underground, capture particles streaming from supernova cores, offering a real-time X-ray of a star's collapsing heart. Yet for all these tools, puzzles remain. Why do some massive stars vanish without a supernova? How do planetary nebulae sculpt their bizarre shapes so precisely? The next generation of instruments like the Vera Rubin Observatory's All-Sky Surveys or the Athena X-ray mission aims to crack these mysteries by catching stellar deaths in their earliest moments. Because in astrophysics, every answer peels back a new layer of questions, and every dying star we study rewrites the rules of cosmic evolution. Despite all we've learned about dying stars, the cosmos still guards its deepest secrets closely. Take supernova. We know these explosions happen when massive stars collapse, but the exact moment of detonation remains elusive. Computer simulations can recreate the collapse, but something always stalls just before the explosion. Some hidden physics, perhaps turbulence or quantum effects we don't yet understand, must provide the final push that turns a faltering collapse into a full-blown supernova. It's like knowing every ingredient in a recipe except the one that makes it finally rise in the oven. Black holes pose even thornier puzzles. We understand they form when massive stars collapse, but what happens in those final milliseconds when matter crosses the event horizon? General relativity predicts a singularity, a point of infinite density where physics breaks down, but quantum mechanics suggests information can't simply vanish. This paradox has birthed competing theories, from Hawking radiation to firewalls to holographic universes. Even more perplexing are intermediate mass black holes, the missing link between stellar remnants and supermassive giants. Are they grown from star collisions, or do they form through some unknown process in the early universe? Then there's dark matter's shadowy influence. This invisible substance outweighs normal matter 5-1, yet we've never directly detected it. Its gravitational pull shapes galaxies, but does it also affect how stars die? Some theorists suggest dark matter particles might accumulate in stellar cores, subtly altering fusion rates or even triggering premature collapses. Others propose that dark matter annihilations could explain mysterious gamma-ray bursts with no visible supernova. What keeps astronomers awake at night isn't just these unanswered questions, it's the surprises lurking in the data, like stars that vanish without exploding, leaving only a faint infrared glow. Or supernova that appear 50 times brighter than physics allows, defying all known models. Even neutron stars, those ultra-dense city-sized objects, keep shocking us. Some rotate nearly 1,000 times per second, while others have magnetic fields strong enough to atomize a human from 1,000 miles away. The tools we're building to solve these mysteries are as extraordinary as the puzzles themselves. Next-generation gravitational wave detectors will listen for collisions we can't see. Neutrino observatories buried under Antarctic ice may catch particles from the next nearby supernova, and space telescopes like the upcoming Nancy Grace Roman Observatory will scan millions of stars simultaneously, hunting for the subtle changes that precede stellar death. Yet for all their complexity, these cosmic riddles matter far beyond astronomy. The gold in your jewelry, the oxygen in your lungs, even the calcium in your bones, all were forged in stellar explosions. Understanding how stars die means understanding our own origins. It's a reminder that we're not just observers of the universe, but active participants in its ongoing story. Every atom in our bodies carries the legacy of stars that died billions of years ago, and every new discovery about their deaths rewrites our place in that grand narrative. Every breath you take contains oxygen atoms forged in the furnace of a dying star millions of years ago. The calcium in your bones, the iron in your blood, these elements didn't originate on Earth. They were born in the final moments of massive stars, scattered across the galaxy by supernova before eventually finding their way into our planet's formation. Even the gold in your jewelry was likely created when two neutron stars collided in a cataclysmic merger billions of years ago. This isn't just poetic metaphor, it's hard science. Spectroscopy reveals the same elemental fingerprints in distant nebulae as those found in our own bodies, linking us directly to the cosmic cycle of stellar life and death. What's astonishing is how recent this understanding is. A century ago, astronomers didn't know stars could create elements. Today, we've mapped the nuclear processes that transform hydrogen into helium, helium into carbon, and so on up the periodic table, each step occurring in different stellar environments. The carbon in your DNA might have formed in a red giant's quiet fusion, while the iodine in your thyroid could trace back to a violent supernova shockwave. These connections transform astronomy from an abstract science into a personal story, one where the universe isn't just something we observe, but something we're fundamentally part of. Engaging with this field doesn't require a degree in astrophysics. Start by simply looking up. The next time you spot Orion's belt, remember that the leftmost star, Betelgeuse, is a red supergiant nearing the end of its life. When it explodes, perhaps tomorrow, perhaps in 100,000 years, it will scatter new elements into space, continuing the cycle that made our existence possible. Free apps like Stellarium can help you identify such stars, while citizen science projects like Zooniverse let anyone classify supernova or analyze telescope data from home. For those craving deeper involvement, amateur astronomy clubs offer hands-on experience with telescopes, often hosting public star parties where enthusiasts share views of planetary nebulae or distant galaxies. Platforms like NAS, a citizen science catalog, connect volunteers with real research projects, from tracking asteroid light curves to monitoring variable stars. Even social media has become a tool. Many professional astronomers tweet about breaking discoveries, offering front-row seats to cosmic events as they unfold. The most profound realization isn't just that we're made of stardust, it's that we've evolved the consciousness to comprehend it. In a universe where matter constantly recycles, we're the rare part that can look back and trace its origins. That duality, being both product and witness of cosmic evolution, is what makes astronomy uniquely humbling and empowering. Whether through a backyard telescope or a university research program, engaging with stellar science doesn't just teach us about the stars. It helps us understand what it means to be stardust come alive. Exploring the cosmos doesn't require a PhD or $1 million telescope. It starts with curiosity and a willingness to look up. Local astronomy clubs offer some of the best gateways into this world, hosting star parties where enthusiasts gather under dark skies to share telescopes and knowledge. Picture a crisp evening, strangers becoming friends as they point out Jupiter's moons or the delicate ring structure of Saturn through an eyepiece. These gatherings aren't just about observing, they're about connection, linking personal wonder to the collective awe humans have felt for millennia when confronting the night sky. Many clubs also organize public lectures where professionals break down complex topics like supernova remnants or neutron star mergers into digestible stories, often with stunning visuals from Hubble or JWST. For those who prefer exploring from home, the digital universe is just as rich. NAS are live streams of celestial events, like lunar eclipses or comet flybys. Turn your living room into a front-row seat for cosmic spectacles. Platforms like YouTube host astronomers who explain cutting-edge discoveries in real time, from the detection of gravitational waves to the latest images of dying stars captured by space telescopes. But the most thrilling part you can actually contribute to real science without leaving your couch. Citizen science projects like Zooniverse invite anyone to classify galaxies, track variable stars, or even hunt for supernova in telescope data. Imagine spotting a distant star's explosive death before professional astronomers do. Your name could end up in a research paper. Then there's the joy of simply learning the stories behind the stars. Apps like Sky Safari or Stellarium transform your phone into a portable planetarium, revealing that the bright star you've been admiring is actually Mars or a distant red giant nearing its final act. Books like Neil deGrasse Tyson's Astrophysics for People in a Hurry or Carl Sagan's Cosmos weave the science of stellar life cycles into narratives that feel more like epic poetry than textbooks. And if you're craving hands-on experience, affordable telescopes or even binoculars can unveil breathtaking details like the Orion Nebula's glowing clouds, where new stars are being sculpted from the ashes of old ones. The beauty of astronomy lies in its accessibility. You don't need to calculate a star's spectral class to feel moved by its light, which may have traveled centuries to reach your eyes. Whether you're jotting down observations in a notebook, attending a lecture on white dwarfs, or simply lying back in a field to watch the Milky Way arc overhead, you're participating in humanity's oldest and grandest conversation. Every glance upward echoes the curiosity that drove ancient cultures to map the heavens and modern scientists to unravel the physics of supernova. The universe isn't just something we observe, it's a story we're all part of, written in stardust and light. And so, as we conclude this journey through the lives and deaths of stars, remember, their final acts aren't just in points. They're transformations, scattering the ingredients for new stars, planets, and even life across the cosmos. The next time you gaze at the night sky, you're not just seeing pinpricks of light, you're witnessing an epic cycle of creation and renewal, one that links your existence to the vast, dynamic universe around you. The stars may die, but their legacy shines on in the heavens above, and in the stories we tell beneath them. From the violent explosions of supernova to the quiet fading of white dwarfs, dying stars are the architects of the cosmos. Their lives and death shape galaxies, forge elements, and even create the conditions for life. As we've seen, these celestial events are not just distant curiosities, they're part of our own story. Every atom in your body, every breath you take, carries the legacy of stars that burned bright and died long before our solar system existed. The iron in your blood was forged in a supernova's heart, the calcium in your bones distilled in the slow burn of a red giant's core. Even the gold in your jewelry was likely born in the collision of two neutron stars, a cataclysm so powerful it sent ripples through space-time itself. This cosmic recycling isn't just history, it's happening right now. Somewhere in our galaxy, a massive star is collapsing, preparing to scatter its enriched guts across interstellar space. In another corner, a white dwarf is siphoning material from a companion, inching toward a thermonuclear detonation that will outshine entire galaxies. These events aren't just spectacular light shows, they're the universe's way of reinventing itself, turning destruction into creation with relentless efficiency. What's truly humbling is how interconnected it all is. The death of one star becomes the birth of another, its remnants weaving into the fabric of nebulae that will one day coalesce into new solar systems. The same explosions that could sterilize planets also deliver the ingredients for life. It's a delicate balance, a cosmic dance where every step, no matter how violent, contributes to the whole. So the next time you look up at the night sky, remember, you're not just seeing points of light, you're witnessing the ongoing saga of stellar life and death, a saga that's been unfolding for billions of years and will continue long after we're gone. Those stars, whether blazing blue giants or faint red dwarfs, are the engines of change, the alchemists of the universe, and in their light we find our own origins and perhaps our destiny. Thank you for joining me on this journey through the secret lives of dying stars. If you enjoyed exploring these cosmic mysteries with me, don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep looking up and